Okay, that's interesting. Okay. All right. Looks like it's probably working, most likely. Hopefully. Okay. We'll find out. Let me know, by the way, if you actually access the Panopto lecture recorded lectures, if they came out okay. I know they're not getting the camera's not getting this part here, but I mean the microphone's where it's at. Any questions before I start on chapter 2? Chemistry? Anyone? No reaction? No? Nothing? Okay, that's fine. All right, so I know that when I say chemistry, most of you make that face. I'm aware of that. I promise you I'm going to oversimplify everything, make it real plain and straightforward. But we do have to know how chemistry works in order to understand why the parts of the cell work the way they do, why we use a phospholipid bilayer in order to make a cell membrane. Why not just make it out of protein? Well, we're going to see why that is. So that's what we have to do with chemistry here. So let's start by talking about matter, which is the name for all the stuff that's in the universe, regular stuff. And that all that regular stuff in the universe is made of atoms. You know what they say, don't trust atoms, they make up everything. And atoms, you can see on the periodic table all the different kinds of atoms that we know about. There's a few extra off the end here, but basically these are super heavy and short-lived anyway. All the action, I just realized this door is open. I feel sorry for any other professors who are listening to me for the last 2 hours. So all of these are the different kinds of atoms that you'll see in the universe by and large. And every atom has a nucleus. The nucleus is a word that means little part in the middle. This is a little confusing because in chapter 3 we're going to learn about cells, and cells also have a nucleus, but that's the cellular nucleus. This is an atomic nucleus. The atomic nucleus is a tiny little super dense part of the atom in the very middle. And the atomic nucleus, it has one or more protons. And these protons are in the middle, and then the atom has this electrons going around the outside. Now, this is not to scale. If any of you've ever been to NRG Stadium, anyone been up there to Houston, the gigantic stadium right there? Imagine a marble, put it in the very middle. That's the nucleus. The entire stadium is the entire atom. So the nucleus, I'm drawing it not to scale so you can actually see it, because it's a tiny little speck. But it's super dense. Almost all the mass of the atom is in the nucleus because protons and neutrons have a lot of mass, and they are found in the nucleus. That's most of the weight of the atom is in the very center. The thing about neutrons, have no charge. They are neutral. They're just ordinary little balls of matter. Protons are special because they exert what we call a positive field of energy around them. And that positive doesn't have any connotations to like good, or anything like that. Positive is just the opposite of negative in terms of what this field is called. We could have called it anything else. We could have called it up and down. We could have called it black and white. That might have been racist. I don't know. But like this field of energy, we call a positive field of energy around it. It irradiates outwards from every proton. And that positive field of energy attracts electrons because electrons are the opposite charge. In chemistry, opposites attract, right? So an electron creates a negative field of electrical charge. And when these fields come in contact with each other, that attracts them to the electron and the proton towards each other. Now, they're actually pulling on each other with equal force. But that's like saying you and a truck could pull on a rope with equal force. Guess which one's moving? You, not the truck, right? And so because the proton is so much heavier, what the electrons end up actually doing is they actually orbit the nucleus, orbit the proton. Now, we are used to drawing it in a circle like this. This was the original idea of the atom. Well, not the original idea, but Niels Bohr came up with this, and he said, oh, look, if the electrons orbit the nucleus in a circle and they have levels of energy, it actually makes all the math work out. And then turns out, actually, he was wrong. They don't orbit in a circle. The electrons actually are moving so fast because they're so incredibly tiny. I cannot emphasize enough how tiny these electrons are. These electrons are so tiny and they move so fast that they actually form a cloud. They're like zooming around super fast at all times. But you can kind of think of it like an orbit because it's just this shape going around the nucleus. Right? And so these electrons make up most of the space. They take up this empty space around the nucleus, And so that's what creates most of the space of the atom, but most of the mass is there in the center, in the nucleus. Now, this is one proton and it's one electron. So the atomic number of a atom is the number of protons it has. So if it has one proton, I know what type of atom it is. What type of atom is it? Hydrogen. Up here. See that? Number 1. Exactly right. So if I draw a nucleus with a different number of protons, that means it is a different kind of atom. So I'm going to just put a plus 11 here because I don't want to draw 11 little pluses, but you can use your imagination. If it has 11 protons, what is it? Sodium, Na. See that? Na is sodium. Those of you who don't know, Na is old Latin, stands for natrium. It's the old Latin word for sodium. That's why that's Na. And then potassium's old name was kalium. That's why it's a capital K. Stands for potassium. So this is 11 protons all stuck together. So it's going to attract how many electrons? 11, right? That would make sense. But here's the thing. Do I have it here? Yeah. So here's the thing about the atom. These electrons each have a negative charge. What do negative charges do to each other? Do they attract? No, they repel. Right. So I can only put so many electrons together in one space. Right. And so when I'm going to go back to the Bohr model because it's kind of the easy one to draw. When I start adding electrons to this nucleus, they don't all just crowd around. You might think, all right, let's just put 11 electrons on this bad boy. No, this is not how the universe works for whatever reason. Maybe this would be more convenient, or actually maybe life wouldn't exist if this were the case. But this does not occur. I hope anyone's drawing this because this is not real, right? What's actually happening is that there are slots that these electrons fit into. You can't fit more than a certain number of electrons in an orbital, which is not a vocab word. It's just the name for these slots. So that first shell has 2 electrons, and the next one has 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? How many electrons is this all together? 10. Good. How many electrons can it attract? 11. So I can add one more, right? But that's going to go on the next shell. Shell number 3. This is why chemistry is such a big deal in predicting how the universe works, how our bodies work, how chemicals work, how life works. Because these electrons have behaviors based on what shells they fit into. And where they are and what they want, finger quotes, they're electrons. They don't actually know what they want, but they want things, right? This electron here is lonely. It's all by itself. And if you think about this plus 11 charge, there's 10 electrons kind of canceling it out. So there's only plus 1 charge, and it's kind of a long ways away from the nucleus. So this electron can get lost. Other things can take this electron away. Right? And when you take an electron away, this is no longer sodium. It is now a sodium ion, Na+. Why did I write a plus? Alright, it's got 11 protons and only 10 electrons. So if you do the math, right, negative 11 plus 10, right? Yeah, plus 10. So it's got an extra positive charge to it. That's it. Now, it doesn't suddenly become something else, by the way. So occasionally people get confused. They think, oh, it's only got 10 electrons, so now it's neon. Nah, son. The number of protons, that's a technical term, right? Nah, son, the number of protons determines what atom it is. And here's the thing. We don't really want to change, in general, the nucleus very much. If I could change the nucleus, what kind of energy would be released? You know the word. Nuclear energy, right? That's what nuclear energy is changing the nucleus of atom. Is anyone here, show of hands, is anyone here powered by uranium? No? Any plutonium? Hydrogen fusion? No, of course not. So here's the thing. In biology, we do not mess with the nucleus. We leave it alone. We assume it stays the same all the time. Now, that's not actually true, but when that changes, then, nuclear weapons are going off or nuclear reactors are being powered and stuff. So with living things, we leave the protons alone. We say, okay, if this is going to change, The only thing that's going to change is the electrons. And that's why chemistry is the behavior of electrons, and biochemistry is the behavior of electrons in living things. So when we look at these slots, so I'm going to go take this back to regular sodium. This last lonely electron can get taken away. And if it gets taken away, that's going to change how that atom behaves. So one thing that helps to think about these electrons and their behavior is an analogy to gravity. So let's see. Let me grab a paper clip. Oh, perfect. Here we go. All right. So I have a paper clip. If I let go of the paper clip, what will happen? It will fall. Why? Gravity. Gravity's pulling on it. And it has gravitational potential energy because there's a distance it can fall. Right? So so if I let go of this paper clip, it will release that potential energy, and that potential energy will become another kind of energy, kinetic energy, right? So here's the thing. Protons and electrons work the same way. To learn the details on that, you need at least a year of physics, which you don't have to take. I'm not going to make you. I'm not going to, drag you by the arm down, like, hey, sign up for physics. No, I'm not going to do that. As much as that would be fun, I won't do that. But the basic idea, without the equations involved, the basic idea is the same. I can take an electron and a proton, and I told you they're attracted to each other, right? We already understood that. Opposites attract, chemistry, that whole thing. But when the electron moves towards the proton, it releases energy, right? So as it does this and then goes into its orbit, it releases some kind of energy. Now, if I want to take this electron and put it back out here, if I want to take this paper clip and put it back up here, what do I have to do? I have to go pick it up, and what does that require? Energy. I have to put energy back into the paper clip to pick it up, right? If I want to take an electron away from a nucleus, I have to add energy to it. Right? And this actually answers a question that you didn't know you had, but it stumps people all the time. Why does fire hurt to put your hand in? Assuming that you believe that fire hurts to put your hand in. Why does it hurt? Because it's hot. But why does hot things hurt? Well, you stimulate your nociceptors. That's correct. Yes, very good. But here's the trick as to why that happens. If I add energy to this electron, it jumps out away from the nucleus. And what we're about to see is how electrons can stick together in bonds. And when I have a bond, which I'll actually go ahead and draw right now, the idea of this electron falling towards the nucleus means I have this electron orbiting this nucleus. Here's a hydrogen atom. I'll draw another hydrogen atom. Here's another electron I added to fall towards the nucleus. This electron has already fallen towards this nucleus, and this electron has already fallen, right? It's not gravity, it's electrical force, but it's actually pulled towards this nucleus. The thing is that this electron can now also be attracted to the other nucleus too. Scandalous, right? And when that happens, this electron is now attracted to both nuclei, and this electron is now also attracted to both nuclei, which works for them. It's their choices, their lifestyle. This is now what's called the sharing of valence electrons, or more succinctly named a covalent bond. You've heard of covalent bonds. That's what a covalent bond is. The electrons are now attracted to both nuclei, and in so doing, they have brought the atoms together, and now they stay together unless I add energy. Just like with adding energy to the paperclip, bringing it back up, I can add energy to this, and the electrons will come apart. So that's why fire hurts, because fire has a lot of energy. And when you have energy, you put your hand with a lot of energy, it starts adding energy to all the bonds and all of the proteins and other molecules in your hand. They all stop being close to each other and start being farther apart. and that causes cells to fall apart. And once the cells fall apart, you have pain receptors called nociceptors, which we'll see near the end of the semester. And ow, 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 and your brain goes ow, ow, and you say, okay, I won't do that again, which is probably what you all did when you were between the ages of 2 and 5, I would guess, right? Because all kids find a way to do that eventually. Put a hand on something hot, adds energy to their system. Their brain goes, oh, I don't want to add energy to my system like that anymore, right? So it's a handy lesson learned. So this is a bond, a covalent bond. Now, it's not the only kind of bond. There's a bunch of different kinds of bonds, but the two kinds of bonds we're going to worry about in this class are ionic bonds and covalent bonds. Covalent bonds are the most common for what we're going to look at. Macromolecules are all made with covalent bonds. Water is made with covalent bonds. The vitamins are made with covalent bonds. There's a bunch of things that are made with covalent bonds. There's not a lot of ionic bonds in our bodies for reasons which I'll get to in a little bit. But an ionic bond is a very not hard to understand kind of bond. I don't actually know if this is looking at this. Here, let's go back to our old friend sodium, plus 11. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I said there's this third shell with this lonely little electron. It's already kind of far away, so it wouldn't take a lot of energy to take it away. Then I'm going to draw another atom. I'm going to draw chlorine. Plus 17. 17 protons, right? That's what chlorine here is, number 17. So when I draw 17 protons, or 17 electrons, I'm not going to just draw them in one shell. I'm going to go by orbital. 1, 2 is the first one. And the next one has 8. So 3, 4, 5, 6, 7, 8, 9, 10. And then the next shell has how many more? 8 spots, but I'm only going to draw 7 electrons because I'm at, and I want 17. Right? 1, 2, 3, 4, 5, 6, 7, and 1 empty spot. Now, this is not on the test, but there are periodic trends you'll learn if you ever take real chemistry, where you learn about how this valence stabilization cancels out 10 protons worth, 10 electrons worth. So you have 7 protons pulling on this entire shell. So this spot, it wants 1 more electron, and it will pull very hard to get one. It will take one from wherever it wants. And in fact, it can take this electron from the sodium and add the electron to the chlorine. Now, this is not sodium anymore. Now it's a sodium ion. This is not chlorine anymore. It's a chlorine ion or a chloride. This is now I have a positive and a negative. What do positives and negatives do? Opposites attract. Exactly, right? So I can actually have a bunch of, and I'm not going to draw them because I'm lazy, but I actually have a bunch of sodium and a bunch of chlorines. They could mix, and their atoms could kind of make a lattice, right? So Na plus Cl minus, Na plus Cl minus, right? And in fact, they can make a 3-dimensional lattice, which is going to end up being a crystal. This is actually a crystal that I think all of you should be familiar with. What kind of crystal is this? Salt crystal. This is what's on your dinner table, right? In a little shaker, right? It's this crystalline structure. This is what ionic compounds are made of. Ions that are alternating in some way, making some kind of crystalline lattice, and these positives and negatives all attract to each other. And that's what an ionic compound is. Ionic bonds are these bonds between these ions, right? Because an ion is just an atom with an uneven number of protons and electrons. So this is an ionic compound. This is a covalent compound. The covalent compound I can also draw like with a hydrogen, with a line to another hydrogen. That line means these 2 electrons that are going around both atoms, right? And so these are 2 different ways that atoms will actually form bonds. As I mentioned, covalent bonds is what we're going to spend most of our energy on. The reason for that is that ionic bonds are usually a little weaker. They usually dissolve when they are in an environment with a lot of other positive and negative charges. And for reasons we'll get to in a little bit, that includes water. Is there water in the human body? Yeah, is there a little or a lot? A lot, right? 70% or something like that, right? And so that means that you don't see very many ionic compounds in the human body. Like, for example, table salt. We can eat some salt crystals or put it in our food and eat that. But once this is exposed to water, the water molecules, positives and negatives, right? And these little positives and negatives will actually pull the sodiums and the chlorides off of the crystal until the crystal dissolves. So there's not a lot of ionic compounds in our body. Now, there is a good exception, though. We will get to it later. It's calcium phosphate. Calcium phosphate is the mineral in our bones. It makes our bones nice and heavy and hard, and that is an ionic compound. But salt crystals like this don't stay salt crystals in our body. They dissolve into our blood. Now, sodium, potassium, calcium, those are metals. They're on the periodic table, but we're not used to using them in metallic form. You're not used to seeing like a brick of calcium or a brick of sodium, which would actually explode if you just like pour water on it. What happens is they donate their electrons and then they become minerals that are dissolved in our blood. So our blood actually has a certain amount of sodium, a certain amount of potassium and calcium that if they were dried out, if you took your blood and dried it out, you could make some crystals out of it. But because our blood is mostly water, those minerals are dissolved. They're solutes. They're dissolved freely in the solution. They don't stay in this chunky format. They actually come apart and become free ions, right? That end up doing, right? We have this positive and negative charges, and that actually causes this crystalline structure to dissolve. Now, this is why when we talk about covalent bonds, these are the most important bonds as far as our understanding of the structure of the human body, because most of the major structures we're going to learn about, like proteins, carbohydrates, lipids, those are all made with covalent bonds, right? Metals don't make covalent bonds. They're normally non-metals. So if you look over here, the metals are all the yellows on the periodic table. The non-metals are up here. There's not too many non-metals, but carbon, oxygen, nitrogen, chlorine, those are like the super important ones for life, sulfur and phosphorus, right? So those are the actual nonmetals that make covalent bonds. Those are what's important for our body. We do, of course, need sodium, magnesium, potassium, calcium, but they're dissolved in our blood. They're not making big old compounds. Right? So when you make a covalent bond, now hydrogen's a special case because it only has these two spots here. But when you look at these larger covalent molecules, these larger nonmetals, I'm going to go ahead and erase. I hope everyone's done with the sodium and chlorine show for now. If I look at carbon, carbon is, anyone know what its atomic number is? 6, very good, exactly right, thank you, 6. So then it goes 1, 2, 3, 4, 5, 6, 6 protons, 6 electrons. How many slots are there in the outer shell? 8, right? How many electrons are in the outer shell right now? 4. That's a problem. That means that this atom wants to share 4 electrons, partner up 4 electrons with 4 other electrons from 4 other atoms to make 4 pairs of electrons in order to make a complete outer shell. So, for example, if I take a methane, that's 4 hydrogens. Here's each one is a hydrogen is 1 proton. And I go like this. And then here's another one, electron, proton. This here is methane. I can also draw it CHHH like this. These are the same thing. This is just the long way to draw it. This is what the electrons are actually doing versus this is just, covalent bonds, just as lines, right? This is how most of our body is put together, all the structures, interesting structure of our body. Because it doesn't just have to be hydrogens, I can actually make more carbons, and these carbons can actually be bonded to other things, like, for example, oxygen and hydrogens and even nitrogen, right? Like, this is all legal. All this is completely legal as far as the chemistry is involved. So these molecules are the ones, this is organic chemistry. This is what our molecules of our body are actually made of. Notice all the carbons have 4 lines coming out of them because they want to make 4 covalent bonds. Each oxygen has 2, each nitrogen has 3. Carbon is the king of covalent bonding. So if you ever watch any sci-fi shows and they say it doesn't appear to be a carbon-based life form, what they're saying is it's not from Earth because all of living things on Earth are carbon-based, meaning our molecules are proteins, carbohydrates, and lipids. Nucleic acids are all made with a lot of carbon because carbon makes 4 bonds, and that makes it good for making these long chains, right? So if you have something that's not carbon-based, I don't know what the heck it is, but it's something that we haven't encountered. Something that you could argue about whether it's possible to have life that's not carbon-based, but find any regular life living on other planets that are our temperature or anything like that, it's going to be carbon-based, right? Because carbon does this. Carbon is great for making covalent bonds that can make big chains of things so that the whole can make these different structures that can help maintain homeostasis, right? Because that's what you want, these molecules that can have specific shapes so they can help maintain homeostasis, right? So, all right, questions so far? So far, we're following hopefully a little bit, maybe, yeah. All right. Okay. So one important thing about these covalent bonds. Here I drew methane, which is hydrogens and carbons, but I'm going to change it up. I'm going to switch one of these hydrogens out. I'm going to actually make this guy oxygen +8. So I got my 1, 2. I'm going to go 3, 4, 5, 6, 7, 8, right? So I've got 2 lone pairs of electrons, and then I got another can share with a hydrogen. Here is methane, or this is methanol now. This is I'm going to go ahead and draw here. This guy here is carbon with hydrogens. And then I added an oxygen here. Here's the thing about oxygen. Oxygen has a lot of what we call electronegativity. Electronegativity is a name for how strongly something is pulling on the electrons, right? And so if you have two atoms that are pulling with equal electronegativity, they'll share the electrons evenly. But if I have carbon and oxygen bonded, the oxygen is an electron hog. That is what it's going to do. It's going to pull real tight on those electrons. And so when it does this, these electrons are not actually being shared evenly. These electrons are actually going to crowd around the oxygen and leave the carbon behind. Now, it might be a little weird to think about, but I talked about sharing. Anyone who's shared custody of kids knows that just because you're sharing doesn't mean it's equal sharing, right? Sharing does not have to be 50-50, right? And so the electron sharing doesn't have to be even if the atoms have different electronegativities. And so if I look at something with a high electronegativity like oxygen, when oxygen is bonded to another atom like carbon with a lower electronegativity, this bond, what kind of bond was this here? We said what kind of was this? Covalent. Covalent, right? But this one is not even, right? Correct? It's oxygen to carbon is not even, right? Yeah? So we call this a kind of bond called a polar covalent bond. Now the reason we call it polar, where have we heard the word polar before? Have we heard that word before? Is that a brand new word? Polar bears, right? Where do polar bears live? In the cold area in the North Pole. That's why we call it the polar bear, because it lives in the North Pole. And the reason we call it the North Pole is because there's another pole called the South Pole, right? And so poles are two opposite sides of something, right? And so not all bonds, not all covalent bonds are polar, because not all covalent bonds have a positive and negative end. But if I add oxygen to a carbon, this is now polar, because now the oxygen is the negative side, and the carbon is the positive side. And so that's what's going to create a polar covalent bond, which means that if I put this into a molecule, it may be a polar molecule. This here is a polar molecule, which means it has a negative end and a positive end. Now, not all molecules do this. Not all molecules are polar. Lipids are a good example of molecules that do not have positive and negative ends. They are nonpolar. The electrons are evenly shared. In fact, I will draw for you a lipid right now. It is very easy. All you need is a bunch of carbons and hydrogens. And all of these hydrogens and carbons have equal electronegativities, or close to equal, basically. And so they share the electrons evenly throughout them. Communists, right? And so that means that this does not have any positive or negative charges on it, as opposed to a polar bond that creates polar molecule that has positive and negative ends. Now, one molecule that is the really good example of a polar molecule is water. Now, it's not a macromolecule. It's just a regular little micromolecule. It's just got 3 atoms. But that oxygen, look at it, H2O. The oxygen's pulling on the electrons way way more. The hydrogens become electron deprived. The oxygen becomes electron rich. The oxygen ends up with a negative charge. And that means that water molecules stick to each other. That's also the reason, by the way, I mentioned earlier, ionic bonds come apart in water because these water molecules have positive and negative charges on them that pull apart the ionic compound. There's an important lesson here, by the way, ionic and covalent bonds, right? Because ionic compounds are based solely on attraction, positive and negatives hanging out with each other, right? So if your relationship is based solely on attraction, it'll only last until there's many other attractive things around. Versus if your relationship is based on sharing, it won't dissolve as soon as there's lots of other charges around. So just life lessons for you from biology class, from 8:30 at a biology class. Right? Everyone's already starting to get a little loopy. That's okay. So water molecules mix with other water molecules because they have charges. And then this guy here, methanol, which is wood alcohol. So hopefully none of you ever drank this, but it's a thing that can drink. You can drink this actually. It acts just like alcohol, except it also makes you blind. So don't drink this. Rots your optic nerve. It's weird. I don't know why it does that, but it does. Right? But this molecule will mix with water. Right? You add water to methanol and they'll mix together because this is a positive and negative end, and water has positive and negative ends. As opposed to if you look at a lipid molecule here, if I add water molecules to the lipid, positives and negatives, right? And then positives and negatives, right? Are these water molecules going to mix with the lipid at all? Does the water going to mix with the lipid? Do oil and water mix? Now you know why. Because the oil has not any attraction to the water molecules. The water molecules are attracted to each other. They separate out, right? Same thing with salad dressing, like you take olive oil and like vinegar, which is like it mixes with water. You gotta shake them real good, and even then there's little droplets, and then the droplets come together and get bigger. Because the lipid molecules don't need to be mixing with the water. There's no attractive force. There's no positive negatives to attract them to the water molecules. So that's what we're going to get to next class. I'm going to have one more thing to talk about here, but at the start of next class, I'm going to hit this idea of polarity again, because that's super important for how the macromolecules work, for the different macromolecules. But I'm going to talk about acids and bases for the last part of class, because this is important. You're going to see it now, and you're going to see it on the test, and you're going to see it in 2402 when you talk about acidity and the digestive system and so forth. So I know I just made a big deal about how covalent bonds are sturdier than ionic bonds. But if I look at oxygen, which here, let's see what, I'll draw a water molecule. Plus 8. All right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now I've got an hydrogen molecule here, and or hydrogen atom, and then I've got another hydrogen atom here. Right? Just because, now the sharing here, I mentioned, is uneven, right? Because the oxygen has a higher what? That was a long word. There you go, electronegativity. The oxygen's pulling on these electrons more. In fact, it's pulling so much that it actually makes the bond a little weaker. So the electrons are kind of pulling into the oxygen. Sometimes the proton actually ends up kind of getting left out in the cold. Actually leaves. Now this was water, right? Just like this. But if this bond, which happens every so often, one of these bonds breaks because it gets kind of weak, this is now an H without an electron, so it's just an H plus, and this has 3 lone pairs, so now it's an OH minus. It's called hydroxide. And then this guy here is a hydrogen ion, but actually, what is it really? What's that? It's a proton. So what happens is you've released a proton from the water molecule. Water molecule is broken apart. Now this sounds scary, but actually this is happening all the time, in all water. So if I look at this water ball right here, there's a ton of protons in it loose, right? But every time a proton breaks apart, there's a hydroxide that's also separated. And what's going to happen is it's going to pick up another proton. It's normal. Happens all the time, right? No, you don't see this hydroxide going off and complaining, there's never going to be another proton like that. No, it just grabs another one, right? Right? So water is full of free protons that break off, and these hydroxides just and these protons are mixed in solution and they end up rejoining to another proton to another hydroxide. It happens all the time. So what this has to do with acids and bases is that any chemical that adds protons, adds free protons, is called an acid. So acid has a scary sounding name because we think of it as, oh, that's something like in a cartoon, like it sizzles and burns your arm off. Well, there are acids like that. Orange juice is an acid, right? Vinegar is an acid. Actually, this is mean, but I did it because I was a little mean. There was a makeup sales lady at the store once that was kind of harassing me a little bit because I was with a lady, and so I was like, oh, we got this thing. So I took the bottle. I'm like, hey, this has ascorbic acid in it, and I looked at her accusatory. She's like, oh shit. I'm like, I'm just kidding. That's vitamin C. Right? Gotta leave me alone. But ascorbic acid literally is an acid, but it's also vitamin C. It's an important part of our body. And why it's called an acid is because if I have it, I'm going to go ahead and erase my super detailed version. If I just have a bunch of water molecules chilling, some of them will break up because that's normal. You just have a free proton. Here you have a hydroxide. Here's another water molecule. If I add a chemical like ascorbic acid or acetic acid or or carbonic acid or a bunch of other things, what that's going to do is increase the concentration of protons without increasing the concentration of hydroxide. That's what an acid is. That's all it is. So we can measure how powerful an acid is by the pH scale because water at pH 7 is neutral. It has an equal number of hydroxides and protons and free protons or hydroxide of hydrogen ions. So if you look at now, also by the way, fun fact for you may already know, if I instead add a chemical that takes away the free protons, so I end up adding a bunch of extra hydroxides, what do we call this? It's the opposite of an acid. It's a base, right? This is a base. So alkaline chemicals are things that elevate the pH by taking away the free protons, right? So now there's fewer free protons and more hydroxides. The balance is uneven. If the balance is exactly even, it will be at pH 7. That's what pure neutral water is, pH 7, right? That's pure water. If you look at something that adds protons, the pH starts to go to a smaller number, pH 6, 4. Notice that it's going to be rainwater, and then it starts to be tomato juice. Then you get to soda. Soda is actually very acidic. It's pH 3, right? That's why you're not supposed to just drink it by itself because it'll rot your teeth eventually, right? Stomach acid is up to pH 1, which is why people who throw up regularly for any reason rot their teeth also, right? Anemia, the thing that can happen, right? Folks, don't throw up all the time for no reason. It's not good for you. And so notice that it actually goes to pH 0. It actually goes past pH 0. I had a colleague who was a chemist. I was a lab tech at the time, and she showed me scars in her arm. They weren't like hideous. I was like, see these scars? Fluoronic acid. I was like, oh. She's like, yeah. I was working like, chemists have cool scars. I'm jealous. I didn't get scars from studying ecological functions of poppy seeds. And oh well, it's okay. It was very boring thesis. So that's the pH scale. Notice that it goes larger. You start getting to basic chemicals, baking soda, detergent. You stop seeing things you can eat. You start seeing things like cleaners, bleach, oven cleaner, right? Those are very alkaline chemicals that take away protons. And so, sometimes people wonder, why is it that the pH of 7 is the middle? And why is it that a pH of a smaller number is more acidic? Well, that's a good question. I'll answer it with another question. Which of these numbers is bigger, 10 to the negative 7 or 10 to the negative 3? That's a bigger number, way bigger, right? Because this is 0.001, right? 2, 1, 2, 3. Yeah, that's that guy. Versus this is 0.1, 2, 3, 4, 5, 6. Yeah, right? So pH is the concentration of protons, of free protons, but it's the negative logarithm of it. So this is pH 3. 3 is 10 to the negative 3. pH 7 is 10 to the negative 7. So that's why the number gets bigger you have fewer protons. The number gets smaller, pH 2, pH 1, pH 0, then you have more protons because it's a negative exponent, right? So we got to make sure we know which one's neutral, that's 7, and then pH of, a pH more acidic than 7 is a smaller number, 6, 5, 4, etc. Okay. All right, and so one other thing about why this matters is obviously there's different body parts that have different acidities. Does anyone know a body part that is acidic? That's the number one, everyone's favorite. There are other body parts that are acidic. There are body parts that are alkaline, like your small intestines are actually alkaline. So you're going to make sure you know what pH is. Another important factor with pH is that if you mix an acid and a base together, they'll cancel. But if you mix a weak acid and a weak base together, they'll make what's called a buffer. And a buffer resists change in pH. So I mentioned that our blood has carbonic acid in it, and that's an acid. So the longer you hold your breath, the more carbon dioxide you add, the more your blood acidifies. But also, at the same time, it's also true that carbonic acid actually helps keep your blood pH from changing too much, right? You never hear about someone drinking a soda because there's a lot of acid in it. That doesn't hurt you. It doesn't harm you. Even if you go on the all orange juice diet, which I don't think you should do. I think that would be bad for you probably after a while. But you could. It wouldn't kill you. The number one thing would start happening, if you're just sitting there chugging your gallon of orange juice, you're going to start ventilating more. Your blood is buffered so that increase in acid is not going to change your blood pH very quickly. You're going to clear it with exhalation. So that's another thing with buffers. You want to make sure you know that. And then the last concept I need to mention now, you're going to see this going down the road, equilibrium. This idea that the protons split apart from the water and then they get back together again, right? That's called equilibrium. That happens all the time throughout our bodies, throughout all kinds of systems in the world, where I have this double arrow. You've seen chemical reactions with like the double arrow, right? So that means water is constantly splitting apart to proton and hydroxide, and then the proton and hydroxide are constantly getting back together to make water. Sounds like some people I know. And so this is constantly happening in both directions. This equilibrium is, well, you don't need to study this unless you take chemistry, but you do need to understand this word, equilibrium, where the chemical reactions happen both ways, because you see this a lot, especially because I'm telling you these things now, and they're going to matter a lot later, because I don't want to get embarrassed when you're raised in 24 too. Okay, so you might remember equilibrium. You'll be like, no, we forgot that. And you're like, he's going to be like, Rick is such a loser, right? So I'm telling you now, a good example of this is oxygen and hemoglobin. Hemoglobin is the protein in your red blood cells that traps oxygen, but it doesn't trap it permanently. It releases it. It constantly breaks apart and releases. So that's why when you breathe in oxygen in your lungs, it attaches the hemoglobin, but it will detach on its own. As the hemoglobin goes through your bloodstream, through your arms and legs, it releases the oxygen because it's in equilibrium. It's constantly attaching and detaching. Which is also, by the way, fun fact, why carbon monoxide is so dangerous. Ever heard of carbon monoxide? Carbon monoxide, odorless, colorless, doesn't smell like anything or whatever. But if you breathe it in, it binds to hemoglobin and it doesn't let go. It kind of stays stuck. Right? So if you breathe in enough carbon monoxide, it doesn't matter whether you're getting oxygen in your lungs because all your hemoglobin is stuck to carbon monoxide already, and you don't deliver any oxygen. All those spots are taken on those hemoglobin molecules. So that's why carbon monoxide can be the silent killer. Right? Okay. All right. So that is chapter 2. Everyone feeling okay with that? Hopefully, yes, a little bit. No, that's not all chapter 2. It's the first part.